We're going to take a look at the refractory periods of action potentials in this video. So we're going to start with the all or none principle. So this is actually really important. So make sure that you know about this for the exam because this will definitely show up there. So the all or none principle just says that if threshold is reached by those graded potentials, then an action potential will be created at the axon hillock. But if threshold is not reached, then you're not going to get an action potential. And if you do reach threshold, you're going to get the same size action potential every time. So that's the all or none principle. Okay, so action potentials are always going to be the same size. They're not going to be graded in size. They're not going to vary. So it doesn't matter the size of the stimulus, whether it's a big stimulus, small stimulus, it's always going to be the same size action potential as long as you reach threshold. And if you don't reach threshold with those graded potentials, there's no action potential produced. Okay, so the all or none principle, really important. So that's with action potentials. Here's a picture of the all or none principle. So on the bottom, we've got some stimuli that are pretty small, and they're going to be opening up some ligand-gated channels in the dendrite here, or it could be in the soma. And the sodium ions that they're letting in, they're not letting in enough sodium ions to reach threshold by the time we get to the axon hillock where these voltage-gated sodium and potassium channels are. So we don't reach threshold, that magic number of minus 55 millivolts, to open up the voltage-gated sodium and potassium channels to start an action potential. So that's an all or none principle. We didn't reach threshold, no action potential. But our next stimulus is large enough that the graded potentials that we do produce, we do reach threshold at the axon hillock, and we can open up those voltage-gated sodium and potassium channels, and we do create an action potential. Okay, so all or none principle, if you do reach threshold, you do get an action potential. If you don't reach threshold, no action potential. Okay, and the other thing that the all or none principle says is that it doesn't matter how big the stimulus is or how small the stimulus is. As long as you reach threshold, you're going to get the same size action potential. So you can see these two stimuli here are different sizes. So let's say the smaller one, let's say someone pinched your arm. And then the bigger stimulus, let's say someone punched you. Okay, so notice that the pinch and the punch, you get the same exact action potential size. Okay, even though the size of the stimulus is very different, you're going to get the same size action potential. Okay, so the brain is actually not going to use the size of the action potential to tell it how big the stimulus size was. Okay, it's going to use something else instead. All right, so this is also part of the all or none principle, that you're always going to get the same size action potential. So if you reach threshold, doesn't matter how big the stimulus was, you're always going to get the same size action potential. Okay, refractory periods. These are really important to know as well. These will also show up on the exam. So refractory periods, they've got two phases, and the absolute refractory period is going to be occurring during the depolarization phase and through most of the repolarization phase. And this is a period of time when you cannot have another action potential stimulated during this absolute refractory period. And then the relative refractory period is going to start right at the tail end of the repolarization phase and then through the after hyperpolarization phase. And you could get another action potential during the relative refractory period, but you've got to have a lot bigger stimulus than normal. Okay. All right, so let's take a look at the absolute refractory period first. So this is going to be from depolarization phase of the action potential through most of the repolarization phase. And during the absolute refractory period, you cannot have another action potential during the absolute refractory period. And the stimulus could be gigantic, like your foot got ran over by a car. You could not get another action potential during the absolute refractory period. Okay, so it doesn't even matter how big the stimulus is, no way you could get a second action potential during the absolute refractory period. Okay, the reason this is because these inactivation gates on the voltage-gated sodium channels, they're still closed and they haven't been reset yet. Okay, so if we look here on the bottom, you can see where the voltage-gated sodium channels started before the action potential at the resting membrane potential. This inactivation gate was actually open, but then when the action potential was stimulated, we've got the depolarization phase. That inactivation gate is open right now, and we've got sodium rushing into the cell, causing the depolarization phase. And then during the repolarization phase of the action potential, that inactivation gate is closed, and so sodium can't come in. And then towards the end of the repolarization phase, as the membrane potential is getting towards the resting membrane potential, the voltage-gated sodium channels will reset again. So they'll go back to their original conformation, how they started. And then once they get back to where they were originally, then you can trigger them to reopen again, and then you can have another action potential. But until you reset them towards the very end of repolarization, you can't trigger them to open and you can't get another action potential. So that's why during that absolute refractory period, you can't get a second action potential, because they haven't reset yet. Okay. Okay, the relative refractory period, this is at the very last end part of repolarization phase of the action potential, and then during the after hyperpolarization phase. So you could get a second action potential, but the stimulus has to be a lot stronger than normal. Okay, so what's happening is that your voltage-gated sodium channels, a lot of them have reset, so you can stimulate them to open again. So here's our voltage-gated sodium channels. So they have reset. So you can get them to open, but the problem is that, remember, at the end of the action potential, you've got this after hyperpolarization phase. And so you're more negative than that minus 70 millivolts, the resting membrane potential. And you've still got some of your voltage-gated potassium channels open with potassium leaving. And so that's making it more negative. And so maybe your resting membrane potential, maybe you're down here, at minus 80 millivolts or minus 90 millivolts or something like that. And so to get all the way up here to minus 55 millivolts threshold, you've got to let in a lot more sodium ions than normal to get all the way up to threshold. So you've got to have a lot bigger stimulus than normal. You've got to open up a lot more ligand-gated ion channels to get all the way up to threshold. So that's why you've got to have a bigger stimulus than normal to get an action potential going in the relative refractory period. Okay, because you've just got a lot further up to go to get to the threshold. Okay, and then here's just a nice picture of where these refractory periods are on the action potential. So you can see the absolute refractory period. That's going to span all of the depolarization phase of the action potential and then most of repolarization. Okay, so during this time, you cannot get another action potential no matter how big the stimulus is. And that's because you haven't reset those voltage-gated sodium channels yet. And then the relative refractory period, you can get another action potential generated here, but you have to have a much bigger stimulus than normal. Okay, and you can get another action potential going here because you have reset some of the voltage-gated sodium channels back to their original conformation. But you need a bigger stimulus than normal because your membrane potential is hyperpolarized. Okay, because your voltage-gated potassium channels are still open, potassium's leaving, and you're more negative than the minus 70 millivolts. So it's going to take more sodium coming in to get up to that minus 55 millivolts to get to threshold to trigger an action potential. Okay, and then this is just a picture from your book. It's kind of a strange picture, but it's just saying that during this absolute refractory period, there's no stimulus. You know, it can be gigantic, but you're not going to get another action potential during the absolute refractory period. And then over here, during the relative refractory period, you can get another action potential, but you have to have a pretty big stimulus. But then as you get towards the end of the relative refractory period, then you get back to the normal size stimulus to generate the action potential. Okay, so consequences of these refractory periods. So this is why with the all or none principle, why all the action potentials are the same size. So why the action potentials So because of these refractory periods, you can't add them together. So remember the graded potentials, we could add them together. Remember we had temporal and spatial summation, we could add those graded potentials together. So remember we could have stuff like this, and then we could get up to threshold with the graded potentials. You can't do that with the action potentials because by the time that you're out of the absolute refractory period and you could generate another action potential, all of this is gone. And so if you stimulate another action potential here and you start to go up again, there's nothing left to add on to. You know, this is all gone. So it's going to be the same size action potential as what you had before. Okay, so because of these refractory periods, this is why in the all or none principle, all of the action potentials are the same size. Okay, even though you have different size stimuli. Okay, so how does the brain tell how big the stimulus is? It's going to use something called frequency coding. Okay, so if you have a bigger stimulus, like somebody punched you versus just lightly touched you, the brain's going to look at the frequency of action potentials coming into the brain. So the more frequent they're coming into the brain's going to say, oh, that's a stronger stimulus. Okay, and we'll look at that. And then also because of the refractory periods, the action potentials can only go one way down the axon. So if we have our axon here, here's our axon terminal at the end. Here's the rest of our neuron here. If our action potential starts here, it's only going to go one way down the axon. It can't go backwards, okay, because of these refractory periods. So that's important as well. All right, so I would definitely know these things. So let's take a look at frequency coding, how the brain tells how big the stimulus is. So we've got some different size stimuli down here on the bottom. The first one is too small. Maybe you've got a bug crawling on your arm and you don't realize it. And the graded potentials that are produced are too small to reach threshold at the axon hillock, and so you don't generate an action potential. And then our next stimulus, maybe someone is just lightly touching your arm, and the graded potentials are big enough that you do generate an action potential, so you are aware of that in your brain. And then our next stimulus is even bigger. Now someone is pinching you. And so now we've got several action potentials going to the brain. And so because the action potentials are more frequent going to the brain's going to interpret that as a bigger stimulus, a pinch versus a light touch. And then maybe someone punches you in the arm. Okay, and now you're going to get even more frequent action potentials, and the brain's going to interpret that as an even bigger stimulus than the pinch or the light touch. Okay, and what's actually happening, you can see that all of these action potentials are of the same exact height. They're all the same size, but notice that our graded potentials, okay, some of them are staying above threshold for longer periods of time, aren't they? Okay, and what's happening is that if your stimulus is stronger and you're maybe doing spatial or temporal summation here, so maybe we're doing some spatial summation, and maybe these neurons are all firing here and opening up some ligand-gated sodium channels, and we're letting lots of sodium in. Okay, and if we keep stimulating those and letting lots and lots of sodium in and keep generating graded potentials over and over again, maybe like with our punch here, then we can keep our axon hillock above threshold. And so when we come out of that absolute refractory period at the axon hillock and get into that relative refractory period, we can stimulate another action potential right away. And then that can make the action potentials more frequent. So that's what's happening with the stronger stimulus. Okay, and here's just another example of frequency coding. So what they've done is they've taken a frog leg and they're measuring the action potentials in the sciatic nerve, and they've hung some different weights on the frog leg, and you can see that the smaller weights, not as many action potentials going up the sciatic nerve, but as the weight gets heavier and heavier, you can see that the action potentials get more and more frequent, right? So that's going to send a signal to the brain saying that, hey, the stimulus is a lot bigger. That weight is a lot heavier on the leg. Okay, and so the brain will interpret that as a bigger stimulus. So that's frequency coding, how the brain tells how big the stimulus is, because the action potentials are all the same size, but it's the frequency of the action potentials that changes, and that's how the brain tells how big the stimulus is. Okay, propagation of action potentials. They go one way down the axon. And the other important thing is that the action potential itself does not travel down the axon. What's going to happen is we're going to create an action potential at one part on the axon, and then that will stimulate the creation of another action potential at the next part of the axon, and then we'll create another action potential, and so we're just going to create action potentials all the way down the axon. Okay, and we're not going to be able to go backwards and create an action potential back behind us where we just were because of the absolute refractory period. Okay, so the reason that action potentials only go one way down the axon and they travel, towards the axon terminal here and don't go backwards, so we can't go this way, is because of the absolute refractory periods. Because you can't generate another action potential during the absolute refractory period. Okay, so let's just take a look at some pictures here. All right, so we've got our axon here, and we've generated some graded potentials in the dendrite or the soma, and here's our axon hillock. And let's say that we've reached threshold and we've triggered the opening of our voltage-gated sodium and potassium channels here at the axon hillock. All right, so we're going to create our action potential here. So we've got our voltage-gated sodium channels opening, and we'll depolarize and then repolarize and after hyperpolarize, and so we create our action potential there. Okay, and so these sodium ions that are rushing in are going to flow down to the next portion of the axon, and they also will go backwards as well, so we'll have some going this way too. And the sodium ions going to the next portion of the axon will then reach threshold at the next portion of the axon, and then that will cause this next portion of the axon to reach threshold. Sodium ions will rush in as those voltage-gated sodium ions come in, and we'll create an action potential right next door. And then those sodium ions will flow back as well, but we're not going to create an action potential where we just had one because we're in the absolute refractory period back here. So we can't go backwards and create another action potential where we just were. Okay, but these sodium ions will flow this way, and then we'll create another action potential here. And so you can see that we're just going to create action potentials all the way down the axon until we get to the axon terminal. But we can't go backwards because of those absolute refractory periods, because we can't stimulate another action potential where we just were because we haven't reset those voltage-gated sodium channels yet. Okay, and where we had the axon hillock here and we've got some sodium ions flowing back into our soma and the dendrites here, we're not going to get an action potential in the soma and the dendrites though, because remember there's no voltage-gated sodium and potassium channels in the soma and the dendrite, right? Okay, so we just have the voltage-gated sodium and potassium channels in the axon hillock and down the axon, right? Okay, and then this is just a nice picture just showing you in blue where our action potential is occurring, and we're just going to create it all the way down here, down the axon as we travel down. And the red is where we've got our absolute refractory period happening. So you're not able to create another action potential behind you, so you can't go backwards with your action potential.